And I'm going to start today, in the interest of trying to get you guys useful information, by talking about oh, you guys know that I put up a Chapter 4 recap video? Did you guys see that? I put it on Google Classroom. Chapter 4 is not super complicated. Chapter 4 is mostly just derivatives and strategies. So we had the derivatives of the inverse trig functions. We had the derivatives of exponentials and logarithms, which I think were all the new derivatives. I gave you guys all blue sheets to write derivatives on last week. Yes? No? Yeah. Okay, good. I put, fill those up with derivatives. Just helps you remember them, and after a while, as you look at them, you won't have to look at them anymore, because you'll be like, oh yeah, yep, I remember that one. I remember that one. And then the strategies, and this is sort of the part that I want to focus on a little bit, is solving strategies. Because you got quite a few possibilities. And one of the things that I see on a regular basis is people will see something in a problem and go straight for that something. Oh, look, there's an inverse tangent. Good, this is a derivative of inverse tangent, and they write down the derivative of inverse tangent and then on to the next problem. They don't stop and analyze the problem carefully to see if it's more than just inverse tangent. So like the first thing they see, oh look, there it is. Here's an example. I've had people solve that problem by just saying, oh look, inverse sine. Well, they know that the derivative of that is that, and so then they just write that, and boom, they're done. Instead of looking at it and backing off a step and saying, well, hang on a second, I've got a function multiplied by another function, and so this is a product rule problem. It's really easy to see the first thing, and you reckon, oh, I know this one, and boom, off you go. And you end up getting the wrong answer because you're not using the appropriate strategy. So step one of solving one of these problems is to slow down just a little bit and think about all your different strategies. Okay, what kind of problem do I have here? So we have to think about the basic rules of derivatives. And those rules of derivatives are, for example, that if I have a constant multiplier, I can move that constant out front. So if I have 3 times some function and I want to take the derivative, well, that's 3 times the derivative of the function. So this also applies to that. Because if we think about what this actually is, this is 1/3 times the function. Oh, constant multiplier. So the derivative is 1/3 times the derivative of the function. On a regular basis, I see students say, oh, look, a quotient. U is equal to f of x, v is equal to 3, v du minus u dv divided by v squared. And they go through all this long, complicated process. But the derivative of 3 is 0. And so now they've just made it complicated instead of saying, well, I don't have to deal with that derivative of that because it's not a function. You only have to deal with derivatives of functions. That constant should always just be moved out front and ignored, except for the fact that it's there every line as you work your way through the problem. So when you're looking at that, be thinking to yourself, do I see a constant value that I can move out front? F of x times g of x. Obviously, this is Product rule. The example I gave you earlier, where people usually forget this, is when you have a really simple function multiplied by a really complicated function. X times arc sine x squared plus 2x plus 3 raised to the fourth power. That's a product rule, because there's a function and there's a function. It's really easy to overlook the fact that that is a function as you're focused on this really complicated thing right there. So when you're looking at a function and trying to decide what to do with it, there's another question to ask yourself. Do I have two functions multiplied together? And if I do, you need to do the product rule. Quotient rule, f of x over g of x. Again, notice two functions. Had a student a couple years ago, constantly, when asked to take the derivative of 1 over x squared, would say u equals 1, v equals x squared. And what he would then get, u prime equals 0, v prime equals 2x. And he would get x squared times 0 minus 1 times 2x, all divided by x to the fourth. Well, it's not wrong, but it's really complicated, because that's a 0, but then you got to simplify one of the x's, and so then you get negative 2 over x cubed. Well, wouldn't it have been a lot easier to write that x to the negative 2 and then just use the power rule, negative 2x to the negative 3? Boom, you got the same answer without going through a long, complicated process. Morning, Mr. Brand.
I like what you're laying down there. I want to put in the back of my mind a little seed about taking everything off Barry and putting it onto a Google shared folder.
Thank you.
We'll talk Friday.
When you're thinking about using quotient rule, just like when you thought, do I have two functions multiplied together, quotient rule should be, do I have two functions divided? Because if I don't, why would I waste my time doing this long, complicated process instead of this 10-second process? Mr. Brandon's comment, he likes the way we're thinking here. One of the things he's started to do in pre-calc this year, because of the limited amount of time, is he started to talk about what are called algebra hacks. How do you take a complicated problem and solve it easily? He's even showing students stuff online where, hey, if you want to solve a quadratic and you want to use the quadratic formula, there are programs all over the place, including in the graphing for the graphing calculators, where you can just type in the values of A, B, and C, and it solves the quadratic for you. So why would you spend hours solving a quadratic? You do the hack. Hey, I need the answer to this quadratic. Boom, boom, boom. Okay, there's the answer to the quadratic. Because the goal isn't to solve the quadratic. The goal at this point in math is to use the information of the solution to find something out about a problem. And that's will become more and more true as you go on and on in math. You need to demonstrate the product rule. You need to demonstrate the quotient rule. But at the end of the day, if the question isn't use the quotient rule, the question is find the derivative, you want to do it as quickly as possible. Fewer opportunities for mistakes. F of x plus or minus g of x. It's the derivative of that plus or minus the derivative of that. Again, you just got multiple functions added or subtracted together. You can treat them each individually and then add all the results together, and boom, you're done. So this is the sum or difference rule. I'll just call it sum rule because subtracting is a sum. If we think about it. Oh, here's another fun one. The derivative of a constant is 0. And I see this all the time See that constantly. Because 2x, well, we know that one, that's power rule. You know, the derivative of x squared. And then people just write +1. And they forget, hang on a second. We need to take the derivative of each of the things that's being added together, and the derivative of that one is just 1. Common mistake. But again, stop, analyze the problem. What do I have? I have two functions added together. The first function is a polynomial, x squared. The second function is a constant. Oh, okay. Take the derivative of that, take the derivative of that. So keep that in mind. Keep that in mind. Chapter 4. Chain rule. I think chain rule is pretty self-evident. Anytime you have a composite function, you take the derivative of the outer, and then you just will keep working your way in. Okay. Logarithmic differentiation. This is one that throws people. The only time you use logarithmic differentiation is when you have a function raised to the power of another function. You don't use logarithmic differentiation because you have logs in a problem. You don't use logarithmic differentiation because you have exponentials in a problem. You use logarithmic differentiation when you have a function raised to the power of another function. And this is, again, you guys ever have Mr. Schick for math? Now, he likes to talk about the hammer, what do they call it? The hammer conundrum or something like that. That you get a hammer for Christmas and you want to pound everything down. So when you have a hammer, everything looks like a nail. And we see this in teaching math all the time. You know, we teach you addition. Now you want to add everything because it's the latest thing that you learned. Even if this is not an addition problem. It's like, yeah, but we just learned how to add stuff. And so people try to pile on. It's one of the reasons we do the spiraling homework in our CPM curriculum that you guys learned and did all those years. Is because the idea being that, yeah, we just taught you about hammers, and then we're immediately going to give you a problem that uses a wrench so that you won't just get into the mindset of, yeah, I'm going to hammer everything. You got to decide, oh, is this a hammer or is this a wrench? Sort of doing the same thing here. So logarithmic differentiation, e to the x squared is not a logarithmic differentiation problem because this is not a function. But sine x to the x squared is a logarithmic differentiation problem because there's f of x and there's g of x. So again, as you're analyzing what do I have here, if you see function to function, function raised to the power of a function, you're going to take the log of both sides. Preferably the natural log because it's easier, but it doesn't actually matter. All right. I may think of more later, but what I'm going to do now is I'm going to switch over to your questions. And I'll answer your questions here. And if I come up with more thoughts, I will mention them. So what do you got? Homework problems, concept problems, anything you want to ask me, now's your chance. While you're looking, I'm going to go get my calculator book. Yes?
Problem 45.
Which section are we in?
4.4.
4.4, number 45. All right. Ah! Use logarithmic differentiation to find the derivative of that heinous looking thing. Y equals the fifth root. I don't know why they're using logarithmic differentiation for this one. Probably because this is an insanely complicated problem that could easily be done using the chain rule if you had time. But maybe logarithmic differentiation is going to simplify this. How can I write fifth root more easily?
Um, 1/5.
Yeah. I'm going to not copy all that back down again. So this becomes the natural log of the natural log of this. Agreed? Natural log of y equals the natural log of all that. Are we comfortable with the fact that I can then move the 1/5 out front? So I'm just going to do that right off the bat because I don't want to have to write it twice. So now let's take the derivative. Derivative of natural log is? Anyone? 1 over y. Chain rule says times the derivative of y, because y is a function of x. So the chain rule says, and this is implicit differentiation. So anytime you're taking the derivative with respect to x of some function of y, it's the derivative of f times the derivative of y. That's how implicit differentiation works. Okay, now equals. Okay. Oh boy, this is going to be fun. 1/5 times 1 over all that junk. So 1 over all that junk, I'm just going to go straight to not writing 1 over all the junk and just take the reciprocal. So I've got 2x plus 5 cubed over x minus 3 to the 4th times x squared plus 1 times the derivative of all that junk. Agreed? Now it gets fun. Oh, now it gets fun. Because how am I going to take the derivative of all that junk? What have I got? Quotient, isn't it? Function divided by a function. All right, let's see what happens. U is equal to x minus 3 to the 4th times x squared plus 1. V is equal to 2x plus 5 cubed. I'm going to need this space. Sorry, but you know all the rules of derivatives anyway, right? Good. So I'll start with V prime, the easy one. What's the derivative of that? Chain rule says the outer function is what? What's the outermost thing? Or you can start the other way. What's the innermost thing? If I said x is equal to 3, what's the first thing you would do?
2x plus 5.
Yeah, so there's the inner function, is 2x plus 5. So the outer must be the cube. So, power rule, time squared, times the derivative of that, which is 2. So this is just 6 times 2x plus 5 squared. All right. Now, the derivative of u, a little more complicated because OMG, that's a product. So I'm going to come over here and I'm going to go x minus 3 to the 4th times x squared plus 1. And I'm going to call this A and I'm going to call this B. which means that a prime is equal to 4 times x minus 3 cubed. Oh, thankfully, that's an easy one. And b prime is 2x. Agreed? Okay. I just, if nobody nods, then I don't know whether you agree or whether you're thinking about dirt bike racing or whether, you have no idea what I'm talking about. So, product rule says a times b prime plus b times a prime. So u prime is a, x minus 3 to the 4th, times b prime, 2x, plus b, x squared plus 1, times a prime, which is 4 times x minus 3 cubed. Whew! You know what? I could simplify that. I've got a product plus a product. Anything factor out of both of those products? You're nodding yes. Speak.
X minus 3 cubed.
Yeah, I could take out an x minus 3 cubed. I could also take out a 2. So I might as well, because now I'm left with x minus 3 times x plus x squared plus 1 times 2. See how this is getting simpler? Because now I can write this as 2 times x minus 3 cubed times, well, x squared plus 2x squared is 3x squared, and negative 3x plus 2. I know, you're thinking, wait, how's that simpler? Well, it's simpler because it doesn't have this huge long sum. It's just got 3 terms. The 2, a cubed binomial, and a quadratic.
So when it says u prime, it says times 2x, right? It was back up to 2.
Yep.
Where'd the x go? Yeah, I'm right there.
Right there.
Okay.
Cool. So now, let's write the derivative using the quotient rule. V du, v, 2x plus 5 cubed, du, 2x minus 3 cubed, 3x squared minus 3x plus 2, minus u, x minus 3 to the 4th. You see how this is going to simplify? I've got a lot of common terms. And yes, this is insane. But some things are going to go away pretty obviously and rapidly here. U dv divided by v squared. Agreed? Now, whew. I see some things that can go away already. If I factored a 2x plus 5 squared out of both of these, that's a 2x plus 5 squared. That is a 2x plus 5 squared, and I could reduce with 2 of those, agreed? So I factored out a 2x plus 5 squared, brought that out to the end, and then I took that 2x plus 5 squared and I canceled it with, or reduced it with 2 of those 2x plus 5s. We cool with that? So it just got simpler. If I factor out x minus 3 cubed from both of these terms, Do we agree that I could then cancel or reduce 3 of those x minus 3's? So I'm going to factor out an x minus 3 cubed. I'm going to factor out an x minus 3 cubed. And I'm going to reduce those with 3 of the x minus 3's that are on the bottom. It's getting simpler. I have 4 2x plus 5's here, and I've got 3 up there. So I'm going to reduce that. 3 of those and 3 of those. Let's rewrite before we lose too much track. 1/5, so you got 1 over y times y prime. So what do we got left? Well, on the bottom, I've got an x minus 3. I've got an x squared plus 1. And I've got a 2x plus 5. On the top, I've got, and I'm going to reorder them. Well, no. Yeah, I'm going to put the 2 out front. And I've got a 2x plus 5. And I've got a 3x squared minus 3x plus 2. I'm sort of starting to wonder whether that quadratic factors. Because if it factors, that might help us. Minus, I've got an x minus 3 and an x squared plus 1 and a 6. Is that quadratic factor? 3xx. Let's see, it would have to be 2 and 1. So 3, 5, nope. 2, 3, nope, doesn't factor. Too bad. Would have been nice. Unfortunately, because I'm not seeing anything else that'll factor anywhere in that. So my last step is multiply both sides by y. X minus 3 to the 4th, x squared plus 1, 2x plus 5 cubed to the 5th. You could at this point simplify more because I could take that 5th on each of these 3 parentheses and it would give me 2x plus 5 to the 3/5, agreed? And then I could combine that with my 2x plus 5 to the 1 to give me 2x plus 5 to the 8/5. So now I only have one term with an ugly exponent instead of 2. I could combine this x minus 3 to the 4/5 with that, which would give me x minus 3 to the 1/5 on the bottom. 4/5 minus 1. And I could do the same thing with the x squared plus 1. So if I wanted to take the extra step, I could definitely, the top is going to stay all alone. And the bottom, I'm going to end up with an x minus 3 to the 5th. And let's see, x squared plus 1 to the 4/5. And 2x plus 5. What did I decide? 3/5 and 8/5. And then I got 1/5 over here, and then I got all that junk up there. It's not pretty. Do they have a really hideously ugly answer for this in the book? Yeah. So why give you this problem? I think this is a great example. We can make the argument that this problem is a warning. That this is a warning to anyone who's thinking about going into advanced mathematics. This is what you're gonna do. I remember doing an engineering problem, senior year, aerospace engineering was my field. I remember doing a problem that took 4 or 5 pages of close written math work to solve. And that was the same professor that didn't give partial credit. His argument was next year you're probably going to be working for Boeing or Lockheed. And if you do it wrong, then the plane will just crash at the end of the runway instead of flying. So you're going to do it right in my class to get the credit. So at the end of the problem, you know, if the answer was 32 and you said the answer is 32, you got the points. And if you said anything other than 32, you got 0. It didn't matter that you'd made one little tiny mistake in 5 pages of calculations. Now, of course, nowadays, how would you solve this problem if you were a real engineer? Is you'd plug it into Mathematica or Maple and it would do it for you, which would be much, much easier. Boy, is there an easier way to do this? The derivative of y Ooh. 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 I think I'm getting super excited here about a math problem. Let's go back a step. I know this seems trivial, but here, let's do this. Let's do this. Let's not. Okay, so 1 over y times the derivative of y equals 1 over all that times the derivative of all that. Maybe not. But that's the derivative of y, is it not? No, never mind. Never mind, because what I just get, I get 1 equals 1, which doesn't help me. I have to do the work. Guys, here's the takeaway. Thing 1, I'm never going to ask you to do a problem like this. Not in real life. I mean, homework, yeah. I want you to slog through it. I want you to see what's going on. I want you to be thinking about the algebra. It is really, really important that you be able to work through a large, long, complicated problem without losing things, without having a 2 written down and then on the next line not having a 2 written down. Making sure, you know, you said where'd the x go? That was a good question, because if the x had disappeared because you make some stupid mistake, at the end of the day, your answer is completely wrong because on the second line there was an x and you forgot it. You need to be able to go from line to line to line doing your steps. So there's 2 bits there. One is that attention to detail. You can't copy the line wrong when you do the next problem or when you do the next part. That also means that you have to have handwriting that you can read. I'm astounded by the number of students that I have, not in calculus necessarily, But I have had them in calculus that couldn't read their own handwriting. They would write down their solution to a problem, and I'd say, well, what does that say? And they'd say, I don't know. And it's like, well, you wrote it. It's sort of the whole point of handwriting, isn't it? That when you write something down, you can then read it back later. And they'd be like, oh, I don't know. Is that a 5 or a 3? I don't know. But it's your 5 and your 3. What the heck? So as you're moving forward, develop handwriting that you can read and interpret. Show your work. Skipping steps, because you guys have probably always been really good at doing math in your head. You're not going to do this in your head. There's not one single step here that I would say was a good place to do the math in your head, except maybe this factoring. And I don't know whether were you guys able to pretty follow my factoring? I could have written it out as whole new lines where I factored out 2x plus 5s and I factored out x minus 3s. And if I was in Algebra 2, I would definitely have rewritten the whole line with all the factors. But I figured with you guys, I could say I'm factoring out 2 of those and 2 of those and reducing, and you'd be okay with it. But you need to develop good math habits, which means being really careful about copying from one line to the next, about showing your steps, about not losing things, about not being casual about it. All right? Enough time spent on that crazy problem. Did it go like you thought it was going to go? That it was just the problem was is that it was.
Help going through it.
Yeah. Okay. Yep. Cool. Splitting it up into sections is good too. It's like, I did this and then I had the A and B over here, and sometimes splitting it up. You just got to be careful that you're keeping track of your sections. Don't do this. Don't have the main body of the problem sort of going like that around your page and then have a section down here and a section over here and a section in there, because you'll never keep track of the sections. You'll notice that my main body of my problem started here and worked to the bottom of the board. The quotient rule came down to here, and then I had another quotient rule here. So it was very organized. Even with all of this, there was a clear organization to the problem. Paper's cheap. Don't feel like scribbling in a corner is a good strategy because you save paper. Paper's cheap. Have an organizational system, even if there are big blank spaces on your paper, that's fine, as long as you can find all of the different bits of a problem. Okay? All right, wow, woo! That was a fun one. Next, what else you got? Anybody? Nothing? Carter? Nothing? Mila? Okay. All right, guys. 4.4 quiz. It is up right now. I also recognize that you guys haven't had as much time to ask questions and go through this stuff. I'm just leaving them open, okay? But it has been posted. When you take the 4.4 quiz, my A group took it yesterday, and today I'm going to grade them and I'm going to send them their answers. I'm going to give back all their answers so they'll see it as quickly as possible. When you guys take this quiz, I will get it graded and I will get it back to you immediately, because the chapter 4 test opens on Thursday, tomorrow. You have all weekend to do it, but I want you to have the results of that back so that you can look over the 4.4 quiz and make sure that you didn't miss anything or make any mistakes on that prior to taking the chapter test. Okay. I will respond to email questions as fast as I get them. I actually do sometimes check my school mail in the evening because I have my school mail go to my phone as well. so I can respond to, if I see an email from a student and I'm like, oh, this needs to be answered tonight, I will answer it immediately. If it's a question about your grade or something, then you'll hear back from me the next day. But if you email me a question and it's a calculus question and I'll try to answer it immediately. And by immediately, I mean, I go to bed at 9:30. So if you email me at midnight because you're a night owl, you will not hear back from me until the next day. So, but you've got all weekend to do this one. And like I say, that one's just open. I don't think I have it closing anytime soon. But if you wait until the weekend to do the 4.4 quiz, you're probably not gonna hear back. I probably won't be going in and grading stuff over the weekend. So if you want to hold off until tomorrow and take that quiz tomorrow after you've had a chance to ask me questions, I will get those back to you by the end of the day tomorrow. I can answer questions then on Friday, and then you'll have Saturday and Sunday to do the chapter test. And that's probably the best strategy. I'm still just trying to figure out, with everything staggered, I want everyone to be able to take the quiz when they've had an opportunity to do all the work and ask questions, but I don't want to stretch it out too long. Just because, there's just lots of stuff I want to get through in the limited time that we have. On Friday, I'm going to drop the 5.1 videos, and we'll probably have the 5.1 quiz next Thursday. We'll come up. I'm still sort of thinking that, a lot of these we could do quicker if we were all meeting together, but I'm going to try to do a section a week, and then sometimes cram 2 into a week and a half or something, just to try to, when it doesn't make sense to have a whole week for a really short section that doesn't tell us much. So, one of the questions I had the other day was, how does this course relate to Calculus 1 and Calculus 2? So I might as well tell you guys this. Calculus 1 is derivatives, and this is college level calculus. And Calculus 2 is antiderivatives. And then integrals, which is sort of the same thing, but not quite the same thing. We're going to completely finish this. Chapter 5 is a bunch of applications, so using derivatives to do various things. So we will be completely finished with Calculus 1 by the end of this year. We will touch on Calculus 2. I don't know how much antiderivative we'll get to. My thought is that we should be mostly done with Calculus 1 by spring break and maybe the first week of the second round, because I'm going to continue to throw stuff at you. That's a couple sections anyway. So when you head off to college, you guys will be taking both of these unless you can convince your college that you're good. I don't know what the process is for convincing a college that you're good. It might be one of those where if you sat down with your college advisor and said, I took AP Calculus and my teacher said that we were done with this and I'm really confident about it, but I didn't get AP credit because of coronavirus, they might either give you a test and let you go straight into this, or they may just say, sorry, our policy is. You'll find this super easy and you'll get a 4.0 and it'll be a nice boost to your GPA right at the beginning of college. And then on this, like I say, we're going to intro that. We'll start talking about antiderivatives before the end of the year. And antiderivatives is just what it sounds like. Right now, we're finding the slope of a line. An antiderivative says, well, given the equation for the slope of the tangent line, can you figure out what the original function was? So you're just working your way. Instead of here's a function, find the equation of the slope. You're told, here's the equation of the slope. What was the original function? And so, and we'll get into that in more detail when we get there. So there's planning. There's a little bit of overall for over the course of the year. If you guys have no more questions, then you could work on homework problems, work on the assignments, stick up your hand and ask me questions if they come up as you're working. Happy to stop what I'm doing and answer them. We're here till 20 more minutes. And then tomorrow we'll have lots and lots of time. So if you got more questions, bring them tomorrow. Cool.